So in the previous video, we introduced the idea of a stack, and I emphasize the word idea because if you recall, a stack is nothing more than an abstract data structure, which in essence is just an idea or a set of rules that govern data. Now, we mentioned that you could actually create a stack using a number of different concrete data structures like an array or a list. So for our examples, we're going to use an array, but know that a list works basically the exact same way. And going forward, later on in the course, we're actually going to implement it using other things as well, such as things called linked lists, and we'll come back to that later on. Okay, so in order to properly understand all the operations of a stack, what I want you to do is I want you to think about the different data structures we're going to use. So let's start off by thinking about the idea of an array. And there are 5 operations that every stack can manage. So we have our push, we have our pop, we have our top, our size, and then is empty. You can probably surmise exactly what each one of these do, but let's go over them in a little bit of detail first. So push, which has a new item. Okay, let me just erase that a little bit so we can read it a little bit more clearly. My handwriting. So we have a push, which pushes a new item onto the stack. So add a new item on top of the stack. Important that we say on top of the stack. Now, whenever we're trying to visualize these actions, I want you to think about an array. Now, normally we would draw an array in a horizontal fashion, but there's no real rule that says we have to do that. A lot of times we'll draw them vertically as well. You're going to see me draw this setup quite a bit throughout this course because we're going to revisit it for a number of different reasons. So let's assume that we have a stack like this, just an array really. And I'm just going to separate this off. And let's say I've numbered them, so the bottom one is element 0. This is just a way for us to visualize this. Now this implies that I created an array of size 6. Okay? Now it could be as big or as small as you want, depending on the type of problem you're trying to solve. A stack, again, is just an idea. You apply that idea to your given scenario, right? So, for example, if you were creating that back button in a website or a web browser, then how many times do you want them to go back? Is there going to be an upper limit, or can they have 50 million websites in their backup stack? I don't know. Or maybe you're going to say, well, you can only back up the last 3. Okay. So, all right, so let's look at this. Let's assume that we already have a few items on our stack. Let's say we have the number 5, the number 7, and the number 12. Now, I come along and I want to say, okay, well, I want to push the number 9 onto the stack. Now, first up, we need to realize what the current size of this stack is. The current size of this stack is 3. Okay? Now, when I push the 9 onto the stack, basically I'm saying push it on top of the stack. Where do I push it? Well, I'm going to push it to the next index, which just happens to match the same number as our size. So we can use this idea when we implement it as an array. Remember, our index values don't match up exactly, right? So when I want to push this, I'm going to try and push the 9 into this place right here. And I'm going to change my color so we can see this. So our 9 is going to go right in here. So that means that our size is now going to change, and our size is now 4. So our size has been updated to modify to account for the fact that we just added a new item to the stack. Now, this is fine. How would that differ if we were doing this as a list? If we were doing this as a list, I'll do it in blue over here, we wouldn't have a maximum size to our array. Our list is expandable after all, right? So our list would look more like this. In the very beginning, after we've added those 3 elements at the bottom, we would have our 5, we would have our 7, and we'd have our 12, and it'd only have elements 0, 1, and 2. But the size is still equal to 3, and I still want to push 9 onto the stack. Well, when this happens, basically you're calling the add function of your list, right? So what does that do? Well, that creates another element on top. So remember, our list is only as big as we need it to be. So that 9 is going to get pushed onto our list, and then our size, so that gets pushed on there, and then our size gets updated now to be 4 again. So it's basically the same idea. The only difference is it doesn't have that extra overhead of space. Now, of course, a list has its own overhead that arrays don't have to deal with, so it is a trade-off. You have to decide what makes more sense for you. I'll be honest, typically speaking, I work with an array whenever I'm dealing with stuff like this. Just trying to trim things down as much as possible. So that's the way push works. Now you see that in the example here, I'm pushing numbers. But a stack doesn't have to be with primitive data types like integers, doubles, or bytes or anything like that. A stack can be anything you want it to be. You're the one that's implementing it. So if you want it to be a stack of objects, you're more than welcome to do so. Now in the last video, we talked about a few different applications. We talked about the real-world applications of the plates and the chairs. Then we talked about the computer application of a back button inside of a web browser. Well, that would be just as easily applicable to, say, for example, an undo operation in a program. Or you could also use it for a deck of cards, where the stack is the deck itself, and it holds objects, which are cards, not just integers, but actual objects that are cards that have attributes and behaviors and everything along those lines. So it's really up to us to decide what we want to do. All right, so push is the first operation. The next operation is pop, and this is the second most important operation. So pop doesn't have any parameters, but it does have a return type, right? So it depends on what type that your stack is holding. So it's going to return top item, whatever that item represents, top element, top item, and deletes it from the stack. So for example, if we had the stack that you're looking at right here, which is 9, 12, 7, 5, so from top to bottom, if we were to pop an item off of this stack, the 9 would get deleted from the stack, but it would get returned from the pop function. So that way we could store it, we could use it on the fly, depending on what we're doing with it. Okay, so let's take another look at this. Let me draw our stack. And 0, 1, 2, 3, 4, and 5. And we have our 5, our 7, our 12, and our 9. So if I want to pop, this is going to return us the 9. So size is currently equal to 4. So after this operation, let me switch my colors again. So after this operation, size is going to get shifted down to 3. Now here comes the big question. What happens to that 9 that's currently in index 3? Well, to be honest, this all depends on what concrete data structure or what data structure you're using to implement your stack. With an array, we actually don't do anything with it. We leave it there. We pretend it doesn't even exist. So what we do is we just decrease the size. And so that way, whenever we're referring to the size, in this case, we're pointing at size 3, which means the 12. Even though that 9 still exists at index 3, we just basically pretend it doesn't exist. We just ignore it. And the array already consumes this space anyway, so we're not losing anything by doing that. So basically, we just pretend it doesn't exist. Now, if we're dealing with another data structure, we may actually have to delete the item to get rid of it. So we're going to come into this later on when we start talking about linked lists and whatnot, but basically we can physically remove it from memory. We don't actually need to do that in this case, though. We can just leave it as is. All right, so pop basically removes this item, so that means the 9 will get deleted and pushed up and returned with the pop operation. Okay, that's all there is to it. Of course, with all of these operations, you have to be careful. You have to be thinking, well, I can only pop if there's actually an item to be popped. I can only push if there's space for the item to be pushed on the stack. What if the stack has an upper limit? Well, that it might. It all depends on your implementation of it, right? So if you have a stack of, let's say we're talking about that buffet, Well, that buffet may have an upper limit of how many plates can be stacked in there. Maybe it can only fit 20 plates. So if you try and put a plate number 21, it's just not going to fit. So it says no, the push fails. So let's go to number 3. Number 3 is top. So this one's easy. It actually does the exact same thing as pop does, except it doesn't delete the item. It just returns the top item. So it's a way for us to analyze what's on the top. It's almost like sitting at that buffet and just looking at that plate to see whether it's clean or not. If it's clean, then you're going to say, okay, I'm going to use this one. If it's not clean, you might go down, you might remove it to look at the next one and continue on and so on and so forth. So this one just simply returns the top item. There's no and here. That's all it does. So I'm not even going to draw a picture for it because it does the exact same thing as the previous one, except it doesn't delete it and we don't have to change the size. It just simply returns the value. Again, if we're dealing with objects, it's going to return an entire object. If I have a deck of cards, it's going to return a card object. It's not going to return the suit or the rank or anything like that. It's going to return the entire card object. Okay, the number 4 operation is size. Well, there's not much to this. This just returns the value that you currently have stored in your size variable. Now, do you have to store a size variable? Well, you do, unless you want to do a lot of extra work to actually keep track of how many, or how to calculate, how many items are in your stack. You would actually have to pop off each one, count them, and then push them back on the stack. It's probably not something you want to do. So it's better to maintain this. So this returns the number of items on the stack. So the best way to do this is to simply maintain. So every time you push, you add one. Every time you pop, you remove one. And then that size variable is just a simple integer that keeps track of everything. You're not going to return the size of the array, the length of the array, because you might have empty spots at the top. And that doesn't make any sense. If you're doing things as a list, well, that's a little different, because then you can actually return the count of the list. So it depends on the implementation you're choosing, right? So there's no point in keeping track of a length or of a size variable if you're implementing it as a list, because that's already tracked by the list structure as it is. So number 5, well, number 5 is exactly what you think it is. It's a Boolean check, a true-false check on that size value. So returns true if size is exactly equal to 0, false otherwise. So all 5 of these operations should be public functions of the stack class that you create. And you'll be like, well, what does this actually look like in code? So what I did was I developed two code examples for you. One of them uses primitive data structures, as simple as possible. The other one uses an object data structure. So you're actually maintaining a stack of objects. So that's what the rest of this video is going to go over. So if you don't need that, you can stop watching here and you can go on and do the rest of the lesson in terms of your homework and whatnot. So let's go take a quick look. So here is a very simple program. So this is what I called simple stack. And it's made up of 2 classes, my main.cs and my stack class I created called number stack. So let's go into the number stack so you can actually see what it looks like. So inside of here, I only maintain 2 pieces of information about this stack. And pretty much every stack is going to maintain the exact same 2 pieces of information. A size and the array that's going to hold all the stack items. Now this array is holding integers. All right, so this stack is a stack of integers. So I can't put doubles in here. I can't put anything else. It's in a stack of integers. I created this other constant because at some point we're going to be doing things like top and pop, and what if there is no elements to actually return from the top and the pop? We have to give something back to the caller of the function. So in this case, I set it equal to the minimum possible value of an integer. Yes, it is possible that we actually stored that number, but it's very unlikely. So I just created a constant, a public constant called no element. So other classes could actually check to see whether the return value of pop and top was equal to no element. If it is, then they would handle things differently than if they actually got a good piece of data. So my constructor for my stack, in this case, because I'm using an array, I need to set up a size. So I've created this int max size parameter for the constructor for number stack, and that's when I instantiate the stack inside using that size. So basically, I make sure that anytime I push, I don't exceed that size. Otherwise, I'm going to run into a problem because the array is not big enough. And then I also set the size of the stack to 0 because we haven't added any elements yet. Okay, so let's look at the 5 operations. You can see the 5 operations are all here: push, pop, top, size, and is empty. It's pretty short. And every one of your stacks are going to implement these same operations. You might call them something a little different, but it depends on what you're doing. So for example, if I was making a class that represented a deck of cards, so I have a card stack, instead of pop, for example, I might have deal card. Now, in the example, in the object example that I actually do a deck class, but I keep the naming of all of the 5 key functions of the stack to be the same, push, pop, and everything like that, just so there's no confusion. So let's take a look at this. The push function takes a new number to push onto the stack. As long as the size is smaller than the length of the length of the array, it's safe to push it on here. So all I do is assign it to that current element, the current size, which we showed in the diagram, and then I increase the size by 1. This effectively pushes that item onto the stack. I don't have to do anything else. It's just 2 lines of code. Pop. Well, pop, remember, we have to return a value. So I created a result variable that's currently set to no element. That way, if we don't actually find something to pop, that's what's going to be returned, is no element, which we set up top here, which is the minimum integer value. So down here, I only can pop if I'm not empty. So as long as the stack is not empty, we are going to set result equal to the top item of the stack. So it's a stack at size -1. And now here, this is the magic. This one line of code is all that really actually deletes an item off of an array-based stack. All we have to do is just reduce the size by 1. I didn't actually delete the element. There's nothing to delete because I just leave it as is. So I set size -, and that is what effectively removes it. The data still exists. The data is actually still in the array. We're just pretending it doesn't. And that's fine, because the array is taking up the same amount of space regardless. And then when I'm all done doing this, I'm going to return result. Now that result is either going to be the top element of the stack, or it's going to be no element if there was no top element of the stack. All right, now down to top. Top is easy. Top does the exact same thing that pop does, except it doesn't do the size -, because it doesn't delete an element. It just, if there's an item to return, it returns the item. If not, it returns no element. That's it. Now we get to the next two, which are the easiest ones. Size, which just returns the current value of the size attribute, and is empty just returns the comparison of size equals 0. Right? So this statement right here is either going to be a true or a false. So if size is currently 0, 0 equals 0 is a true, so it's going to say is empty is true. Otherwise, it's going to say is empty is false. So that is the stack in as basic form as possible. So how do we actually use the stack? Well, the stack is a class, just like any other class. So we'd have to create an instance of the stack. So let's go over to main.cs. Now, main.cs, I've actually gone through a whole bunch of things here to demonstrate what's going on. Now, the key thing that I want to point out here is this little comment here. I can have as many instances of the stack class as I want, and they each maintain their own data. So what I do to one stack doesn't affect another stack. So to demonstrate this, I've created 2 stacks. One that holds a maximum of 3 elements, and the other one that holds a maximum of 5 elements. Clearing out the screen for visual purposes, and the first thing I'm going to do is I'm going to display the size of those stacks. I'm going to run the code so you can see everything, and I'll walk you through this as we go. So the first thing we do is we display the size of both stacks, which we see is 0 because no items have been added. The next 4 lines push elements onto the stack. So I pushed one element of number 5 onto the stack 1. Remember, it can only hold 3 elements. And then I pushed 3 elements onto stack 2, 7, -3, 17, in that order. So that means the bottom of the stack is number 7. the middle one is -3, and the top of the stack is 17. So in order to show you that this worked, I then outputted the size again. So the size has shifted to 1 element and 3 elements, as we see over on the right here. Okay. So now I'm going to look at the top of the stack. So this is just the top operation. I'm not actually doing anything with that value. I just returned it and I displayed it. So I just said stack2.top. So that gives me an integer back, so it's perfectly fine to concatenate with my text here. So we can see that it's the number 17, exactly what we expected, because we pushed it in the order 7, -3, 17. Last in, first out. The item wasn't actually removed here. It's still there. So the next set of output actually removes it. So it says pop it off. And I stored that popped item off into this variable called top_num. All right, just a regular integer variable. And then the next output statement actually displays the fact that I popped off that number, and now I'm looking at the new top of the stack. So it should be different. So as we look over here, top of stack 2 after 17 was popped is -3, which makes sense because we put it in that order over here that we see. Okay, and finally, the last piece to the puzzle. What I did here was I will move one item from stack 2 and put it directly onto stack 1. So what I did with this command, and sorry, this is the second last thing I did, is notice what is being pushed onto stack 1. I'm pushing the result of the stack2.pop. I didn't store it anywhere. I just put it directly onto the other stack. So remember, the inside is going to execute first, so it's going to pop off the current top of the stack, which is a -3. We just saw this in the previous output. And it's going to take that -3 and it's going to push it onto stack 1. So that means stack 1's top is now a -3. Which the next few lines of code do exactly this. They demonstrate this by showing you the current size of both stacks and the current tops of the stacks. So if we think about this, stack 2 has had its top 2 elements popped off, which means it should have a 7. The only thing left on that stack should be a 7. And stack 1 just had a -3 pushed on top of the stack on this previous line over here. So now when we display everything, we get the size. The size is now 2 for stack 1 and 1 for stack 2. And then the current tops of the elements are respectively -3 and 7. Exactly what we would expect. So you can see how we're actually manipulating these things. Okay. If I tried to push past the last element of the stack, it just wouldn't do anything. Now, in actuality, when I'm actually writing this program, if I'm writing it more robustly, I would probably do something in terms of tell the user when it wasn't possible or something like that, depending on the program that you're building. Okay. All right. Card games are a huge use of when it comes to stacks. So this is a basic, straightforward numeric stack. Let's look at something a little bit more complicated. So this is an object-based stack. Now here, as I mentioned to you before, it's basically a deck class. So let's go look at the deck. So this is my stack class. I just called it deck because that's what it represents. It represents a deck of cards. I could have called it a pile. I could have called it anything I wanted, as long as it makes sense for what I'm doing. Now you'll notice that the constructor for the deck doesn't have any parameters. And the reason it doesn't have any parameters is because I know a deck is exactly 52 cards. Now if I wanted my deck to have different sizes, because maybe I have, maybe I'm making a game like Solitaire, for example, and I have a whole bunch of piles. It might be the 7 piles that are visible, and then another 4 piles on top to put all the ace, 2, 3, 4 out, and so on and so forth as you play the game. So you might have, 11 piles right there, plus another pile for the regular deck. So that's a ton of piles. That's 12 piles. So in that case, they're not all going to have 52 cards. In fact, none of them actually will. So in that case, I would probably actually have a max size put inside as a parameter. It depends on what I'm using my program for. So in this case, I instantiated it as 52 cards because this specifically represents a deck. Okay? So you can see that down below, I have the exact same operations of push, pop, top, at size, and is empty. The difference is that I'm not maintaining an array of integers anymore. I'm now maintaining an array of cards. So let's pause for a second and go take a look at what the card class actually looks like so you can see and how we're dealing with this. So here is my card class. So every card is exactly the same. When you create a new card, you have to give it a rank and a suit. That rank is a number from 1 to 13. The suit is a number from 0 to 3, where each number represents a different suit. 0 is hearts, 1 is spades, 2 is diamonds, and 3 is clubs. I made these as public constants, so when I create an individual card, I can just use these when I create them to keep things simple, and there's no magic numbers. And then the rank, obviously, is 1 to 13, where 1 is an ace, 2 through 10 are regular numbers, 11 is a jack, 12 is a queen, and 13 is a king. So what happens here is when you create a new card, I record those numeric versions of them. And the reason why we do that is because, well, the rank's number actually is its value. So when you're making a game like, I don't know, like solitaire or whatever you're making, blackjack, whatever you're making, the rank's numeric value actually matters. So that's a different thing. All right, suit, I'm keeping track of that one as well for whatever purposes that the programmer may need. And then down below here, I get the string representation of these. So for example, if the rank is a 1, I'm going to set the display rank to be ace. If it's a 12, I'm going to set it to be queen. If it's a 3, I'm going to set it to the string 3, the number 3. So we can see this down here in this simple set display rank procedure that I created. I didn't create it as a function, I set it as a procedure. Inside of here, so it basically looks at it, uses a switch statement, so it runs super fast. In fact, in a single operation, it's constant time. It just sets this to whatever value it is. So if it's a 1, that's an ace, so I just set it to ace, and so on and so forth. If it's none of those special cards, it just gets the string representation. Now some of you are like, Mr. Lane, I know there's better ways. Yes, there most certainly is. There's a ton of different possible ways, but I chose this way to make sure that the demo is clear to everybody reading it, because everybody reading this is very comfortable with switch statements. Okay. Now, going back up to the constructor, because we haven't finished yet, I set the display suit just equal to the array value using that suit number 0, 1, 2, or 3 inside of this simple array of strings. H for hearts, S for spades, D for diamonds, and C for clubs. So for example, if I created a card that was a 3 of clubs, that would mean that rank would have the value 3 and suit would also have the value 3. Right? If it was a 3 of hearts, then rank would be a 3 and suit would be a 0. Okay? So that 0 index would come in here, it would access this array and pull out the letter H. And that's what would take place of the display suit variable. Okay, so we actually haven't done any of, there's no push pop or anything like that because this isn't a stack. It's just an object, just a card object. Down below I've created a few just accessors for all this data. So an accessor for the integer value of rank, a string value of the rank, an integer of the suit, and a string value of the suit for display purposes. And then I created another operation called display text, which returns a nicely formatted version of the string. So when we run this program, you're going to get the rank, and then a vertical bar, and then the suit, just to keep it nice and simple. Okay. Now I can change this format to whatever I want. I can play with that. Just like I could actually put the full word of hearts, spades, diamonds, clubs here if I'd like. But you're going to see why I shrunk it down in a few minutes. So this is our card class. Every single card in our stack is going to have all of this, all of these attributes and behaviors. So going back to our deck class, we have our push, we have our pop, so on and so forth. And you see the logic is 100% identical to the integer version that we created of a stack. The only difference is we're not pushing integers, we're now pushing cards. So I still check to see whether there's enough space. If there's enough space, I push the card onto the top of the stack and I increase size by 1. Nothing has changed. Pop, it goes the exact same way. So here we have our card. I've created a variable. You'll notice this time I still need an error value, a value that represents a bad result, meaning that I tried to pop off of an empty stack. In this case, I used the value null. Null is the term we use for an object that is unassigned. It hasn't been instantiated. So I have this card result which hasn't been set up yet. So this is a null value. As a programmer, I can actually check for that. So when I get the return value of pop, I can say if that value equals null, then do something saying, hey, we got bad data. All right. So inside of here, same thing. If it's not empty, I set result equal to the current top of the stack, top of the deck. And then the same way as before, I just trim it down. I just say size is one less. And I ignore the fact that that other object actually exists. I don't need to care about it. And then I return the result. It's either going to be a null or it's going to be an actual card object. Top, again, does the exact same thing, except it doesn't reduce the size. And then size and isEmpty are literally 100% identical. So how did I actually use these? Well, let's go over to the main.cs to take a look at this. Ooh, man. Here we go. So, here's my big comment this time. Similar to simple stacks, we can have as many instances of an object stack as we want or need. For example, I may have one for a central deck of cards to the gameplay, but perhaps each player has their own stack of cards, like when someone is playing Pokemon or Magic the Gathering, right? So you could do this. But for this example, I'm just going to have a single stack of type deck, okay? Clear the screen to make sure things are set up. Now, first thing I do is just to show you that the deck is currently empty when we first created, I displayed its size. And then after that, I pushed 2 new cards. I pushed a new card, which is a 1, which is an ace, of hearts. And I pushed a 4 of clubs onto the stack, which means the top of the deck is currently a 4 of clubs. So I'm going to run this so you can see. So a ton of output here, but we'll come back. So the deck start side is 0. The numeric rank of that top. So here's the top of the deck. So I stored it in a variable of type card, top card. And now I'm going to display all the values of that card. So first of all, I got its rank individually, its numeric rank, get rank. And then I got its text version of rank, which is a 4, so it's still a 4. Then I got its suit, and then I got its text version of its suit. And then I got the nicely formatted display message. So over here we see the numeric value of rank is a 4. The string value of rank is still a 4. We got the numeric value of the suit, which is a 3, but the string value of that suit is a C for clubs. And then the nice pretty display of top card is 4 vertical bar C, 4 bar C. Okay? So would you ever need to actually display all that data? Probably not, but I just wanted to show you that you had access to all of that. So the next thing I do is I pop 1 card. So only the ace is left, and when we display its data, did I not display that data? Oh, I did it down here. Yes. So first thing we do is we popped off the 4 of clubs, okay? But now down below here, I'm displaying the new top of the deck. And you'll notice the way that I did this. Instead of actually storing top into a separate variable like I did over here, I don't plan on using it again. So what I did was I actually displayed it immediately. So the way this works, it says deck.top, which is going to give me the ace of hearts. And then I call display text on that value. So it's almost like these two things are in brackets. And then we call display text on that element. In this case, an ace of hearts, which is what we see over here on this line right here. After 1 pop, the ace of hearts is on top. Okay, now it's time to do something interesting. So the first thing I do is I'm going to remove the ace of hearts off there. So now the deck is completely empty. Now we're going to fill the deck with the entire actual deck of cards. And the way I did this here is I just did a nested for loop. I said for each suit from 0 to 3. And then inside of that, for each rank from 1 to 13. So think about that. That means for suit 0, add cards 1 through 13. For suit 1, add cards 1 through 13. So because we have our nested for loops here. So that's all I'm doing is I'm just pushing on all 52 cards. Now in order to show you that we actually have to put some work out to actually display them all, you can't just go through. You're not allowed. You can't go to the second element of a stack. You're just simply not allowed. That breaks the rules of the stack. So in that case, we actually have to do some work. So here you see me displaying the size of the deck just to show you that it is actually 52 cards. But then immediately after that, I'm going to display the entire deck. So I did a while loop that I said, well, keep looping until the deck is empty. While the deck is not empty, grab the top card from the deck. So I popped it off. It's not just top, it's pop. So it's been removed from the deck. It's like drawing a card off the top of the deck. And then display all of its values. Top card, dot display text. Again, I could have done this all in one line rather than both those lines, but I just wanted to show you that it was possible. Okay. So now I do this with a write line command, which means every single card is going to get its own line. So this takes up a ton of space. Look at this over here. So we see this big stack of cards. Now you notice that they come in order of the actual stack. So this is actually what the stack looks like, because last in, first out. So the top of the deck is currently the king of clubs. So that's the first thing that gets displayed. Then the next top of the deck is the queen of clubs, and so on and so forth. It's going to go through all the clubs, and then it's going through all the diamonds, and all the spades, and all the hearts. All right? Okay, so that's all fine and dandy, but that's obviously not very usable within a program. Nobody wants to play a game where all the cards are listed like that. So the next one I did was I repopulated the deck again. I pushed all 52 cards back onto the deck. Okay? Now the next thing I did is, instead of displaying them as a big vertical mess, I did something a little bit more clean. I displayed each suit one at a time. So I took all 13 cards from the first suit, displayed them in a nice horizontal line. And then I took all 13 cards from the next suit and displayed them in a nice horizontal line. So on and so forth, till and through all the suits. So it goes through really the same while loop. It's just what happens differently in the while loop. So I'm keeping track of how many cards I've displayed. And you'll see why in a second. So at the very beginning, I'm saying, oh, I'm going to display the next card. So I'm doing a console.write command this time. So it keeps the cursor on the same line. So I'm writing one card at a time. So I do deck.pop.display text, which is exactly what was over in here. Okay? So I displayed that one card using a write command. So the cursor is still on the same line. If I'm at the end of the line, which means if I've gone through all 13 cards, so if I went through 13 cards, go down to the next line using a write line. So it forces the cursor down to the next line. However, if I'm not at the end of the line, put a comma and a space in there just so I can space things out nicely. So what you end up with over here is the end result is king bar clubs, comma, space, queen bar clubs, comma, space, jack bar club, and so on and so forth till we get to the end. There's no comma here because it only does it if it's not the end of the line. Because when it is the end of the line, it says go down to the next line. Simple as that. Dink. In reality, it'd actually be more efficient if I checked these in opposite order, and I should probably change that, but I didn't. And the reason being is I'm going to be doing the comma more than I'm going to be doing the new line. So it makes more sense, so I don't have to go through both comparisons. Okay, so that is an application of using an object-based stack. You're going to be asked to do a lot of different fun operations and brain teasers and problem-solving questions when it comes to dealing with stacks, and hopefully you have fun with it.